Right, so it's that large vessel that comes that loops over the pulmonary vessel, the top that we drew, and it's a very big elastic vessel. And it being elastic is going to be very important. We'll talk about that in a minute. But it's also one of the largest vessels in the body, and so it has to work against the resistance that's found in systemic vessels. And so what we can discern is the pressure in the aorta as it changes, and that's quite useful clinically. When we talk about the blood pressure is a measurement of how the pressure in this very large artery changes, and that can tell us a lot about how the heart works and how the vessels are operating, how the vessels, what the resistance in the vessels look like. Okay. So the first measurement that we can discern is called the diastolic pressure. And basically, during diastole, we have the AV valves closed, right? The AV valves are closing towards the end of diastole. Blood is leaving the aorta, and it's moving away into the systemic vessels. So what do you think is going to happen to the pressure in the aorta? If blood is leaving the aorta, and it's moving out into the systemic vessels, what will the pressure do? It'll drop, right? So the pressure will drop as blood moves out into those vessels. And so it's going to get to the lowest point, and at that point, this is recorded or measured as the diastolic pressure, right? Sometimes called the end diastolic pressure. So the diastolic pressure is the lowest pressure found in the aorta during diastole as blood leaves the aorta and moves out into the systemic vessel. And in terms of looking at this or in terms of pointing this out on the graph, that's going to be this lowest point here. Okay, so the lowest pressure recorded in the aorta at the end of diastole is our diastolic pressure. Does anyone know what number that corresponds to in terms of your blood pressure? Is it the top number or the bottom number? Top, bottom. So it's going to be the bottom number in your blood pressure. Okay, so it's the lowest, it's going to be the bottom. So the next number that we can also discern in terms of the pressure in the aorta is called the systolic pressure. And this is measured during systole. So at this point, during systole, the chamber is ejecting, like the ventricle is ejecting, and the aortic valves are open. So semilunar valves are open, blood is moving into the aorta, and what do we think the pressure is going to do now? It's going to rapidly increase, correct. So the pressure in the aorta during systole is going to rapidly increase, and at its highest point, we record this as systolic pressure. And this is going to be our top number in blood pressure. And so being able to measure the pressure in the aorta is very useful clinically in terms of the blood pressure, and it tells us about how well the ventricle is working, specifically the left ventricle, and again, the state of the vasculature, the state of the systemic vessels. Now, as the aortic valve closes, we have a bit of backflow of blood hitting against the back of that closing valve. And this presents what we call the dichotic notch. So in the pressure tracing of the aortic valve, we can see that the pressure drops off towards the end of ventricular ejection. So this is where blood is leaving the ventricle as it moves into the aorta. And so pressure starts to fall. But as blood hits the back of that closing valve, we get a sharp increase in the pressure. And this is what we call the dichotic notch. And it's a reflection of the backflow of blood hitting against the back of that closing valve. So that sharp sort of rise or spike in the pressure is representative of that hitting the back of the closing valve. Another meaningful measurement that we can get from aortic pressure is the mean arterial pressure. And this is the average pressure that's measured in the aorta throughout the entire cardiac cycle. So unlike systolic or diastolic pressure that was specifically looking at the pressure at a specific time in the cardiac cycle, the mean arterial pressure is an average of what the pressure in the aorta looks like throughout the entire cardiac cycle. And what that number tells us is the driving force that's moving blood throughout the body. How effectively is the heart pumping blood throughout the body? So again, the mean arterial pressure is a very useful number clinically at telling us about cardiac efficiency. How effective the heart is pumping, how much driving force it's sending blood throughout the systemic circuit. You want to keep in the back of your mind that the entire function of the heart is to pump blood to the systemic vessels. Okay, so the mean arterial pressure can tell us how effectively that is being done. Now, as we talk about the cardiac cycle, I've been speaking about it in phases, so phase 1, phase 2, phase 3, but I want you to understand that there's continuous blood flow throughout the cycle. So this is a very synchronous process. It's a flow, right? It's not interrupted the way we've been discussing it. And so when you look at the artery, the structure of the aorta is a large elastic artery. And so the aorta has this ability to absorb some pressure. Okay, so when blood moves from the ventricle into the aorta, there's an absorption of some of that energy, absorption of some of that pressure. And that stored pressure is in the walls of the aorta and keeps the flow of blood uninterrupted in that vessel. Let's talk about what I mean. Let's look at this slide. Okay, so during diastole, we have the ventricles ejecting blood, the semilunar valves are open, and so there's a continuous flow of blood moving out to the systemic organs. What happens during this time is that this elastic artery, as it expands, it's going to absorb some of that energy. It's going to absorb some of that pressure, and it's going to store it like a pressure reservoir. And it's going to keep that pressure for the diastole phase. And so during diastole, when the valve is now closed, one would expect that there would be an interruption in the flow of blood, but there is not. There's not an interruption here because some of that stored pressure is now released as this vessel recoils onto itself, and it keeps the flow continuous. So there's no interruption in the blood flow to the systemic organs, although there is a brief period where the valve is closed, and we would expect that there's an interruption. That recoil of the vessel generates some pressure, which keeps the flow continuous. Okay? And so the take-home message here is that there is no interruption or block in the flow of blood to the systemic arteries or the systemic vessels at all points during the cardiac cycle. That flow is continuous. Okay, any questions so far? Any questions on? All right, so let's move on to talk about ventricular volume. So this is where we get into a little bit of calculation, and we're going to talk about measuring some of the volumes throughout the cardiac cycle. So the end diastolic volume is a measurement of the amount of blood that's in the ventricle at the end of diastole, right? And so what that number tells us is how much blood has filled from the atria into the ventricle. Okay, what point of the cardiac cycle do you think we measure this number? What point of the cardiac cycle do you think we would measure end diastolic volume? Phase 1, 2, 3, or 4? It would be at the end of 1 or throughout 2. Now remember, the volume in 2 does not change. So if you measure the volume at the beginning of 2, it would be the same volume at the end of 2, the same volume at the end of 1. So you can measure end diastolic volume at the end of phase 1 or at the end of phase 2, same volume. End systolic volume, on the other hand, is the amount of blood that is left in the chamber after the ventricle has ejected. So what is left back in the ventricle after it has squeezed its blood out into the vessel? Now, sometimes we're tempted to believe that all the blood leaves the heart. All the blood never leaves the heart. There's always a reservoir or a reserve of blood remaining at the end of the ejection phase in that ventricle. And so that measurement of blood is called the end systolic volume. Now, we can easily measure how much blood was actually ejected by measuring those two volumes without actually physically going into the vessel and seeing how much blood is ejected. And so if we have the end diastolic volume and the end systolic volume, we can arrive at the stroke volume. So the stroke volume is how much blood was actually squeezed from that chamber. And so to calculate it, of a typical end diastolic volume of about 130 mLs, and if we subtract the typical end systolic volume, which is usually left of 60 mLs, we are left with 70 mLs. And so that 70 mL represents how much blood was actually squeezed out of the ventricle and into the aorta, into the chamber, into the vessel, sorry. Okay? I hope that makes sense. Now, you won't be expected to actually calculate these or memorize any figures, but do understand what each of these volumes represent in terms of when they're measured in the cardiac cycle and how we can calculate the stroke volume from that. All right, another meaningful measure that we can deduce is the ejection fraction. So the ejection fraction is a ratio of how much blood was pumped out of the body compared to how much was filled. All right, and that's our ejection fraction. So if you take the stroke volume, which is how much we actually squeezed out of the chamber, and we use that as we calculated that as a fraction of the total end diastolic volume, we would determine how much percent, what percent of the blood was squeezed out with each heartbeat. So if we do the typical calculation, so for a typical healthy male, about 70 mLs is the stroke volume divided by about 130 is the EEV. We get about 54%. And what that number tells us is that with every heartbeat, 54% of the blood inside of the chamber is squeezed out. Okay, so a large chunk of, or a large portion of the blood actually remains in the chamber at the end of each cardiac cycle. And if you look at the volume tracing here at the bottom, so at the start of, where is it? At the start of atrial contraction, this would be the beginning of diastole. So the chamber is filling at this point. And then if you look at the volume here, this is ventricular ejection. So the volume rapidly drops off. And what we filled to begin with is 130, that's our end diastolic volume. After we dump some of the blood out, what we're left back with is about 60 mLs, that's our end systolic volume. And so our stroke volume is this difference, which is usually about 70 milliliters. And again, if we use the fraction, the ejection fraction, 70 mLs divided by the total end diastolic volume, that's our ejection fraction. That's the percentage of blood that was actually pumped out with each cardiac